All right. Hey, hello, good morning, good afternoon, good evening, whatever time of day you're deciding to watch these set of videos. So the next video you're going to watch actually about amphidromic points and tides has a lot of the usual kind of announcements that I would normally have. If you're watching this in spring 2024, we just didn't quite get to all of the things that we would normally have gotten to by this time in lecture. This is just a short little snippet. So with all of that said, let's just go ahead and get on into it. No messing around here. All right, so we left off, actually, let's go back to the big screen. We left off in class talking about tides and we glazed over what causes them. This video will actually kind of dive a bit deeper into that idea, but we also talked about some of the patterns that we see in terms of how the tides rise and fall. And if we were to look at a tide gauge throughout the course of a 24-hour period, what we would see around different parts of the world. So there were three types of patterns. We recognize there's diurnal, semi-diurnal, and mixed semi-diurnal. And if you recall, here in California, we observe a mixed semi-diurnal signal. That means that there's two highs and two lows in a 24-hour period, but those two highs and two lows actually occur at different heights. So definitely refer back to the slides if you were perhaps not in class or just need another refresher on that idea. So be sure to identify that as needed. So what we are going to talk about here is kind of a more visual representation of what we would see in the tides and kind of why exactly they happen. So here's a neat little representation or kind of like schematic in a way of how the Earth rotates and then where the moon is in regards to the Earth's rotation as well. So this is a little bit maybe of an odd point of view if you were considering Earth. So instead of looking at like a side view like we normally do, right, and looking at like the Americas, like in the satellite images that we show at the beginning of class for our current weather discussions, we're looking like straight at, where we are. But this particular schematic or image is looking at the top here being the North Pole. So that little X is the North Pole. So we're looking at the top of Earth. And we know that the moon, for all intents and purposes, is extended out from the equator. I don't think it's exactly at the equator, but it's out there. And so, the idea here is that wherever the moon is, there's this equal and opposite pull, gravitational pull. And so what we're looking at in this particular case, we have tidal bulges on either side of the moon, where the moon is at, and we have this little Men in Black looking person. It's the vibe that it gives me, hanging out at one particular point, at our starting point. We'll say that this starting point is midnight. So starting point is midnight, and the Earth is going to continue to rotate, and this person we're going to say is stationary, is not going to move. So as this person makes an 8-hour turn, this person goes from being at high tide to being at a low tide. So we start at, say, at midnight, 8 hours later, the person is now here after that rotation, and we start at this high tide, and then about 8 hours later, we're at this low tide space. And then this person travels around, the Earth again, another turn, I guess, another 8-hour turn, and that person then goes through a high tide period, and then is back at low tide, though, at about 8 hours later. And then that person again will continue until they get back to their starting point 24 hours later, which is one solar day. The thing with the moon, however, the moon is rotating, but it has a different time period or a day than the Earth does. So the moon day, one lunar day, is actually one solar day plus 50 minutes. And this is kind of another reason why our high tides and low tides kind of shift by a few minutes each day. It doesn't happen exactly at the same time every day. There is a little bit of a shift just because our rotational cycles are not the same. So hopefully this visual kind of helps with that. So in one rotational period, the person goes around one time, but the moon has also shifted a little bit as well. So it's just kind of an interesting way, I think, to help visualize what would happen and the way the person would go around these tidal bulges. So this is now representing or bringing forth the idea of adding the sun into the mix, right? So the sun is a huge part of our solar system, a huge part of, our day-to-day life, but it's also a huge part of tides as well. It has a massive gravitational pull. That's why it has 9 planets rotating around it, Pluto, I've never forgotten about you, don't worry. And so the top part of the schematic is just referring back to the size of each of these items. So the moon and versus the Earth versus the sun. That's obviously not an accurate representation of how close we are to each other. This bottom part is a little bit better of a representation. But where the moon is located in reference to the sun also has a really large pull on our tides. So moon has its cycle, right? We have the full moon cycle, new moon cycle, and everything in between. We have our quarter cycles as well. So it turns out when the moon and the sun are in that same plane and their gravitational forces are working together, we actually see higher than normal high tides and lower than normal high tides. Those are something called spring tides, and I have the definition on the next slide. Then when we're on the quarters, that is just what we call a neap tide. So, and that's kind of a little bit kind of in the middle, I guess, if that makes a little bit more sense. So when they're working together, it's called spring tide. When they're opposing each other, it's called neap tide. And there's sort of this kind of in-between moment as well. So here is a representation of these ideas, or I don't want to say verbal representation, but like a slide representation. So I encourage you to maybe give the video a little pause so you can write these things down as needed. So I've already talked a bit about the spring and neap tides, but there's one that I did not talk about quite yet, and that's this little buddy right here. It's called king tide, and perhaps you've heard this term before. This is when in our northern hemisphere winter, we're actually closer to the sun. It's called the perihelion phase. So if we're closer to the sun, the gravitational pull is going to be greater. Thus, there's going to be an even larger tidal bulge or gravitational bulge. And so the tides will be even higher. High tides will be even higher and low tides will be even lower. Here in San Francisco, it can actually cause some problems sometimes. Like right by the ferry building, oftentimes there will be signs up that say, hey, king tide, there may be minor flooding on the Embarcadero. Especially if it's like a kind of a stormy day. This happened back in 2023. It was just kind of a wild time. And then the king tides can be even greater if there are periods where the moon is even a little bit closer as well. So if the moon is a little bit closer and we're a little bit closer to the sun, sheesh, we have lots of gravity pulling the water. So here's a visual representation of spring tides. So I think this, in my eyes, this helps. I'm a very visual person, so this helps me when you're talking about, having the power of the moon and the sun working together, causing these tidal bulges to be even more intense. Whereas in a neap tide, they're working against each other, so the tides are somewhat normal in a sense. So if we were to look at a tide table, this is from actually last year, but this is a tide table for San Francisco, I believe. But I think this really nicely represents like what we would see. And one of the reasons why I really like this particular image and the website that I used for this is because it has the moon cycles shown here as well. And notice, much like a lot of things in earth science, it's not an instantaneous reaction, right? So notice when we have a full moon, which in this case is April 16th, we don't see the peak of this spring tide until in between basically the 18th and 19th of April. So it's not an immediate thing. It's not like, oh God, every full moon will be the highest of the high tide. Not necessarily. So I just thought that was kind of interesting. I also just visually really love this image. I think it really nicely shows, of course, the mixed semi-diurnal signal that we see here. But also, if you focus your eyes a little bit, you can see some of these other like mini wave or larger scale, I guess, wave patterns within the rest of the waves, right? And I know I've gone on about this before, but everything in our universe is waves. And this is no different, right? So it's just the patterns that we're observing and just creating more waves within the waves that are creating and causing waves. Everything is waves. I'll keep saying it until I'm blue in the face. So I also want to just compare a few tides around the world. This is an image from your book, actually. So we're comparing Port Adelaide here at the top to Port Adelaide, which is in Australia, and Puquoy, China. And it's going through the month of September, and it's just showing the tide variation here. So I encourage you to pause the video, try to see what sort of patterns you observe. Which one do you think is a diurnal cycle? Which do you think is a maybe semi-diurnal or mixed semi-diurnal cycle? And really being able to recognize that. And then again, just seeing the overall wave patterns within the smaller wave patterns that are just waves. It's just so stinking neat. So yeah, study this image, see what you get, and tell me what you got. Last couple of things I want to touch in on, and if we're talking about tides, we have to talk about one of the largest tide variations in the world, and that's in a place called the Bay of Fundy. So the Bay of Fundy is located just off the northeastern coast of the U.S. So the state of Maine is right here, and Nova Scotia, which is a state in Canada. So this is a little bay basically in between those two regions, and much like, the San Francisco Bay, but it's much more narrow. It almost, to me, kind of gives Red Sea vibes, just like with the little split here. But basically, in a typical daily cycle, the further in you go into this bay, the greater the tidal variation, average tidal variation. So the deeper you are into the bay, if you get all the way in there, you can see a variation of about 50 feet in one day, a 50-foot variation in one stinking day. That is just so wild to me. Whereas at the mouth of the bay, so the closer to the ocean, that variation is much less. Only about 20 feet of variation. And here's just a visual representation of what that can look like. I'll try to maybe find a couple of videos of tidal boring, which is when the tide is coming in. It looks very kind of ominous. It's like this group of waves kind of coming into an area, but it can happen pretty dang quickly. So I'm sure you can imagine that you really got to pay attention if you're a fisherman or if you rely on the tides to do really anything in your day-to-day life. So pretty wild, I think, to me. And it's just a very extreme version of what we see on a daily basis. Last idea in terms of tides and when it can really matter, this time in terms of natural disasters. So think back to when we talked about a really large natural disaster that is one of my favorites, only because it's so large and in charge. And I know it causes a lot of damage, but they're very pretty. And to recall back to what that is, of course, tropical cyclones. And then if you recall back to what the most damaging part of a tropical cyclone is, take a guess. And if you recall that it's storm surge, you would be absolutely correct. So storm surge, of course, is the biggest concern with tropical cyclones when they make landfall. But if a tropical cyclone makes landfall during the peak time of spring tide, and even worse if it's also king tide, which generally doesn't happen as much just because we're not quite in that phase, but it can still be a high spring tide. It can make the flooding even worse, right? Because if you already have waters that are, 3-4 feet above normal mean sea level, and then you have storm surge of anywhere from 12 to 15 feet added on top of that, that is just an enormous amount of water that can do an enormous amount of damage. The example that I have here is Hurricane Laura from 2020. This hurricane made landfall in Lake Charles, Louisiana, which is basically kind of right on the border of Texas and Louisiana. I encourage you to look up where that location is, especially if our geography is a little bit rusty. So a really big concern here was that Hurricane Laura made landfall at peak spring tide at midnight. So not only was a tropical cyclone, a very powerful tropical cyclone, making landfall at night, which is horrifying enough, it was also doing it at the same time that the tides were even higher. So some of the flood damage actually reached parts inland, maybe anywhere from 60 to 70 miles inland. Granted, Louisiana is very flat; it's kind of marshy, whatever. But the floodwaters were still lapping at the doorsteps of a friend of ours. Dad lived like 60 miles inland, and he was getting inundation, from the oceans from this particular storm. So oftentimes when the National Hurricane Center is looking at giving advisories to locations in terms of landfall of tropical cyclones, they certainly take this into account. So they take the tides into account when accounting for storm surge. So we don't have control over that, right? So it's a very interesting concept to keep in mind, and that does indeed is kept in mind. So those are kind of the ins and outs of tides and why the patterns occur the way that they do. The next video, you'll learn about something called amphidromic points, and then we'll dive into yet another chapter of the oceans. Thank you so much for watching.